The aim in this module is to show that the nested intervals property together with the Archimedean property actually imply completeness. Without further ado, let me state the theorem. Let F be an ordered field that has both nested intervals property and Archimedean property. Then F is complete. What I mean by F as nested intervals property is that intersection of nested closed intervals is always non-empty. And what I mean by Archimedean property is the corresponding conclusion in the statement of the Archimedean property that we saw holds true for this field F. Now, this theorem's proof is very important in the sense that the idea behind the proof makes it very clear why we need both nested intervals property and Archimedean property to ensure that there are no holes. What we are going to do is we are going to get better and better approximations of the required least upper bound for a set and show that the intersection of all these approximations is going to be the required least upper bound. That's the basic idea. So what we do is start with a set that is bounded above. Let S subset of F be a non-empty bounded set. Non-empty set that is bounded above. Set that is bounded above. We want to construct the required least upper bound. We proceed as follows. Let M1 be any upper bound. That's a good place to start. And let S be an element of capital S. Take any element in capital S, set I1, which is A1, B1, to be just S, M1, the closed interval S, M1. Now, what is the rationale or the logic behind this choice? Well, clearly, if the set S has any least upper bound, it has to lie in this interval S, M1, no choice. S is an element of the set, so it necessarily, the least upper bound has to be greater than S, or at least as large as S, greater than or equal to S. And it has to be less than or equal to M1 simply because M1 is any upper bound, some upper bound, and the least upper bound is always less than or equal to any choice of an upper bound. So the required least upper bound has to be in this interval I1. Now we'll make this approximation better by setting M2 to be equal to A1 plus B1 by 2. Look at the two endpoints and just take the mean of these two, A1 plus B1 by 2. Now, if M2 is also an upper bound for the set S, then choose I2 equal to A2 B2 to be equal to S, M2, else I2 equals A2 B2 is nothing but M2, M3. What is the logic behind this choice? If M2 is also an upper bound, that means we have found an upper bound for the set S that is smaller than M1 for sure. So we have a better upper bound. And if M2 is not an upper bound for the set S, then we have moved the left hand point of the interval, we have moved it to M2. That means we have chosen an element that is closer to the required least upper bound. Essentially, what we have done is, irrespective of which choice we take for I2, the size of I2 is half the size of I1. So we have moved to a better approximation of the least upper bound. Okay. Now, having chosen I1, I2, Ik to be AK, Bk, choose mk plus 1 to be equal to AK plus Bk by 2 and Ik plus 1 to be equal to AK mk plus 1 if mk plus 1 is an upper bound for S, else Ik plus 1 is equal to, the plus 1 should be a subscript, Ik plus 1 is going to be equal to mk plus 1 Bk. Okay. In this way, we successively construct the required nested intervals. Now, observe that by very construction, Bk, so this Ik plus 1, I will again call it AK plus 1, comma Bk plus 1. By construction, you can prove this rigorously by induction if you want to, but it should be very, very obvious to you that Bk plus 1 minus AK plus 1 is nothing but Bk minus AK by 2, which by induction will be equal to B1 minus A1 by 2 par K. Okay. So what has happened is, at each stage I2 will be half the length of I1. I3 will be 1/4 the length of I1, and I4 will be 1/8 the length of I1, so on and so forth. Here the length of the interval is just the right end point minus the left end point, the intuitive length of the interval. So we have that these intervals are shrinking. Now it's an easy exercise for you to show that n is always less than 2 par n. This is a very, very easy exercise. You can show this by induction. Once you have that, we'll have that these ii's are a sequence of nested shrinking intervals. Okay, let me not use the word sequence. I will just use ii's are nested shrinking intervals. Okay, therefore by the nested shrinking intervals theorem, we must have a unique point in intersection of I equals 1 to infinity, say let's call this U. Let's call this single point U. Now, I want you to do the following. Pause the video, look through the notes where we proved the nested intervals theorem, the Archimedean property, the nested shrinking intervals theorem, and so on, and make sure you understand that both the nested intervals property as well as the Archimedean property are indeed being used to conclude that there is a unique point U in the intersection. So in this one statement, I'm actually compressing several steps. I'm leaving it to you to unwind these steps. It's very important that you do this exercise. Please do that. Okay. So at any rate, we have found a point U. Claim is that U is supremum of S. How are we going to show this? Well, we use the fact that our choice of IIs were not arbitrary, but we were making better and better approximations. How do we do that? Now, suppose S0 is any element of S. Okay. Now, first of all, observe that each BI by our construction is an upper bound for S. That's how we constructed each one of the IIs. We ensured that the right endpoint is always going to be an upper bound of S. That's at each stage we had two possible choices. We always chose that possibility that ensures that the right hand point of each one of these intervals is always an upper bound. Okay, so we have chosen the right endpoint as always an upper bound. Now suppose S0 in S and assume U is strictly less than S0. Suppose we have to show that U is the least upper bound. First of all, let's see that U is in fact an upper bound. We have chosen U to be less than S0. Okay, we want to reach a contradiction to this. Now note that this means S0 minus U is greater than 0. S0 minus U is greater than 0. Now choose N such that B1 minus A1 by 2 power N is less than S0 minus U. Again, note that to choose such an N, you have to use the Archimedean property. Please pause the video. This is a subtle point. Make sure you understand how the Archimedean property comes into the picture here. First of all, the fact that N is less than 2 power N is used, and then you use the Archimedean property to construct N so large that B1 minus A1 by 2 power N is actually less than S0 minus U. Okay. Now that means In, which is AN BN, satisfies Bn minus An is less than S0 minus U. Okay. But U is an element of In. In fact, U is the unique element in the intersection of all the INs, not just this particular one. Therefore, Bn cannot be an upper bound for the set S. Why is this the case? Well, here at this juncture, let me just draw a picture. We have this interval AN BN. Okay. We have this point U, which is somewhere inside. We know that Bn minus An, this length, is certainly less than S0 minus U. Okay. That means S0 cannot be in this interval, because the entire length of this interval an bn is itself less than s0 minus u. So u plus s0 minus u has definitely got to be greater than bn, because the length of this interval is itself just maximum going to be s0 minus u, right? In other words, s0 has got to be greater than bn. Okay, so this shows u is an upper bound. U is an upper bound. What remains to be shown is that it is the least upper bound. So if V is another upper bound, that is smaller than u, then we apply the same trick in a different manner. Then again choose n so large that b1 minus a1 by 2 power n is now less than u minus v. Okay, less than u minus v. Now consider in. Okay, again, if you carefully look at our construction, the left endpoint of any in can never be an upper bound. That's exactly the way these intervals in were constructed. The right endpoint will always be an upper bound. The left endpoint will never be an upper bound. That's exactly how this was constructed. Okay, please check that. Once you have that the left endpoint cannot be an upper bound, same picture with a slightly different orientation will finish the proof. We have a and bn. Again we have u here. And we know that this n has been chosen so large that the size of a and bn, which is same as b1 minus a1 by 2 power n, is less than u minus v, which means that v has to be to the left of a and bn. Again, it's the same logic. This completes the proof. We have shown that this u has both properties of a supremum. It's both an upper bound and it's also the least upper bound. Okay, so we have shown that nested intervals property plus Archimedean property actually implies completeness. Now, why is this very crucial? It's because if you carefully look at the proof, we had used nothing basically to show that you can approximate the least upper bound in the first step. We just chose one point in the set and chose one upper bound. We know that this least upper bound, if it exists, has got to be there. Okay. Then in the second step, we again chose a better in the sense that the length of the interval is becoming half, better approximation. The crucial point is the Archimedean property shows that these approximations get better and better and better. In other words, what is really crucial in this proof, apart from the nested intervals property, is the fact that 1 by n, the quantity 1 by n, can actually be made as small as possible. In just a few modules down the line, as part of next week's chapter on sequences, you will see that the Archimedean property actually implies that 1 by n converges to 0. Don't worry if you don't know what converges means, it will be made clear in the next chapter. So the Archimedean property makes 1 by n close to 0, and it's the Archimedean property that in fact says that as you keep increasing this n, the approximations become better and better and better. So the way we have used these in tandem is to use the nested intervals property to produce the least upper bound, but you can apply the nested intervals property in the first place to get a unique point solely because the Archimedean property allows you to keep improving the approximations. So this is hopefully clarifies the remark towards the end of the last module that we need both the nested intervals property as well as the Archimedean property to ensure that there are no holes. So essentially the Archimedean property is used to surround the hole by really close approximations. You will always be able to approximate a hole just with the nested intervals property. Nowhere do I actually use the Archimedean property to construct these INs. But the fact that they sort of zero in on the hole is made precise by the Archimedean property. So I hope this theorem, even though it's not really going to play any role in this particular course, clarifies completeness to a reasonable extent. Now, what have we done? We have shown that a complete ordered field has no holes. But several questions remain. Our aim was to produce an appropriate ordered field that models the real line. Question is there at least one complete ordered field? Right? All this theory will be a waste if there is no complete ordered field. Second, is there a unique one? Is there a unique one? Okay. The answer to both questions is the following theorem, which I will not prove. Let me, after stating the theorem, illustrate why I won't prove this theorem. There is one and only one complete ordered field, which we call the real numbers. Real numbers R. Okay. When I say one and only, I must be precise up to isomorphism. I will not make precise what isomorphism is. If you have taken a course on linear algebra or abstract algebra, probably it is clear to you what this isomorphism means. So there is essentially only one complete ordered field which we are going to call the real numbers. Okay. Now why am I not going to prove this theorem? Because the proof is really long. In fact, if you want to write a complete proof of this, it will take a small textbook. Indeed, there are many. The notes refers to my favorite one that gives the complete proof. And it really doesn't clarify anything that is needed for later analysis. This is one of those theorems that needs to be proved for the theory to have any validity. If there is no complete ordered field, the whole theory is nonsense. So you need to prove this theorem, but the details of the proof are fairly boring that there is no point in engaging in this activity right now. Moreover, once you take an abstract course on metric spaces, you will be able to show this in a much easier manner. So I'm not going to bother proving this now. I'm going to leave this proof to you. If you are interested, you can look at the references in the notes. Okay. One final point to address. We have produced a complete ordered field. It certainly does not have any holes. But our aim had nothing to do with completeness or ordered fields or anything right at the beginning. All we wanted was we had this real line. When you put the rational numbers in the real line, there are holes. We want to plug these holes, right? Whether the final structure that plugs these holes is an ordered field or a complete ordered field, or it's a topological space, or it's a donkey, is completely irrelevant to us. We want to somehow fill all these holes. Now we have filled all these holes, but how do you know that what you got in the end, the real numbers, has anything to do with the line that you started off with? We have done, in fact, I've said that the construction is long and hard, and I'm even skipping the construction. why should what we have, the real numbers that satisfies all these axioms, why is it not a plane or a sphere or some other complicated object? Why is this exactly the real line? Well, that is something that I don't want to get into. Again, please check the note for references. To show that the real numbers correspond to the real line, I mean, I shouldn't really be using the real line at all because I'm assuming what I want to show as right implicitly in my language itself. To show that the real numbers model a straight line, we first have to understand what a straight line is precisely so that you can show that both are same. Okay. Now it turns out the correct way to do this is to axiomatize Euclidean geometry. Here we go again. I will not bore you with another set of lectures with axiomatization, so don't worry. So you will have to model the Euclidean geometry that you have studied in school via axioms. It will turn out under a particular axiomatization, which makes perfect intuitive sense, the real numbers do correspond to points of a straight line. For more details, please check the notes for references. This is a course on real analysis, and this is the module titled NIP plus AP implies completeness.